attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
My name is Sam Privett. Just want to say this is my third time at CppCon. This is my first time presenting, and it's just an honor to be up here on the stage with you all today. Thank you for coming after lunch. So the title of today's talk, yep. Thank you. All right, let's get serious, huh? The title of today's talk, Why is my build so slow? Compilation, profiling, and visualization. That has been the question on my mind for the last year or so. Quick disclaimer, the views and opinions I'm expressing today are solely my own, not those of my employer, Johnson & Johnson. What are we going to be going over today? We're going to have a quick introduction. I'm going to talk about a few assumptions. We're going to get into how you can actually visualize compilation and the tools with that. We're going to talk about individual problems with single files that can slow down your compilation, project-level problems that can slow down compilation, some higher-order solutions that can hopefully mitigate some of these, have a little section for takeaways, and then we'll have time for questions at the end. I've got about 55 minutes of content, so if you could just hold your questions till the end, that'd be great. Okay. So who am I? My name is Sam Privett. I'm a robotics software engineer at Johnson & Johnson, and I kind of got curious about compilers not too long ago, which was the inspiration for this talk. So what is this talk, actually? Well, like I said, we're going to be talking about visualizing compilation with Ninja and Clang. We are not going to be talking about how to speed up compilers. That is outside the scope of this talk. But we are going to be talking about how we can write code that compiles faster. So a few assumptions I've got here. In general, the lines of code has a somewhat linear relationship to your build time. This is because your compiler needs to actually process and parse the source code. It needs to tokenize it and build the abstract syntax tree. And so the more lines of code you have, the longer your builds. This is another big assumption here. In general, for as long as your software is useful, my claim is that there will be pressure to increase the number of lines of code in your project. This can be in the form of bug fixes, new features, what have you. But over time, your lines of code will generally be growing. And therefore, transitively, your build times will also be growing. Now, if you actually go out and plot your build times over time, like end of the day, what's my build time over a month, you'll probably actually look something more like this. It's not a straight linear line. There's periods of increase, there's periods of decrease. Maybe we started refactoring, maybe we found some dead code and we deleted things. But in general, we're actually going to be increasing. The trend line, again, as long as it is useful or used by others, there will be pressure to increase. And this is kind of a boiling frog problem. The boiling frog, if you're not familiar, is this idea that a frog in a pot of water and somebody is slowly increasing the temperature, and the frog has all the capacity to leave the pot at any time, but it never does, and it ends up perishing because the water is too hot. This is pretty morbid. That's not actually true either. The frog will leave, but it's a good way to describe the problem we're talking about here, where you may not actually notice the problem until it becomes extremely painful. So let's talk about developer productivity. When you have long build times, it's kind of great, right? You get to go to the bathroom a lot, you get to get coffee, you get to talk to people, water, walk around, and I'm compiling, there's nothing I can do. But over time, you may actually notice that you're not really as productive as you may think you are. And I kind of attribute this to not being able to enter the flow state. And now the flow state is a term from sports psychology where athletes are so honed in on their craft that they aren't really cognitively thinking much. It's just kind of going through the motions, and they're things are just happening and they're not really thinking about why they're happening. And when you're writing code, I believe you can get into a similar kind of flow state where solutions just kind of come to you as you're working on things. And long builds kind of get in the way of this. It kind of breaks this feedback loop we have of writing code and testing code quickly. So how do we actually visualize compilation? Well, first, to ground everybody, if you are using CMake, Ninja, and Clang, your build will look something like this. I have 3 source files here. I call CMake. It generates Ninja build files. I invoke Ninja somehow, either directly or through CMake. Ninja then goes out and calls Clang 3 times for my 3 different source files, and then calls the linker to link all my output objects into my final binary. And when Ninja does this and invokes those commands, it saves this really cool .ninja log file. This tracks the start and stop time of the various build commands in milliseconds, stores the name of the output file, and then the hash of the command used. So a hash of the compiler command, the linker command, or some other custom binary can run here as well. And this is a lot of information. This is by default on. If you build with Ninja, this is in your build folder somewhere. This is part of the mechanism Ninja uses to tell if your build is dirty. So you have this. What can we do with it? Well, I'm going to use Privett for this talk. Privett is an open source tool from Google, and it is an interactive trace viewer. It's web hosted. You can go to ui.privett.dev, check it out. If you're not comfortable doing that, you can always build and run the server locally as well. It supports the Chrome event tracing format JSON, among other things. And it's got a plethora of features. There are many other interactive trace viewers you could use to visualize a lot of the things we're going to be talking about today, such as speed scope or even Chrome tracing. But I chose Privett for some of the additional features, and we'll get into that later. So what does it look like? I can take my .ninja log file and just UI Privett, dump it in, and I get this nice time trace. So to ground you a little bit here, along the top, we've got kind of the total time of the build, the timeline. So from left to right, that is the order of the build. We've got 4 distinct zones marked here, and these zones are the actual time of, it is the total time of how long it took to create that object. So it's hard to see, sorry about that, but the highlighted one here is my main CPP. You can see it's distinct. The next one is my other source, the other, and then finally at the end, the orange one is the linker. And this is cool. So we can visually see and get a gut check understanding of what's going on in my build. It's single core, 3 similarly sized files. If you ran this on your build, you'd probably find and see that, oh, one of these object files is pretty big. That's useful. But you might not actually know why that object file is so large. Just identifying it isn't always enough. Well, thankfully, Clang, as of, I believe, 9.0, ships with this ftime trace flag. And the ftime trace flag generates an accompanying JSON file based on the output file name. So for every .o file, you'll have some .json file. And this .json file is in that Chrome event tracing format I mentioned earlier. And it contains detailed information on where the compiler actually spent time. So real quick, before we actually show this, just want to ground everybody on Clang's kind of architecture. When you invoke Clang through Ninja, or just in general, you take your input source file, it gets fed to the front end, creates the abstract syntax tree, which is essentially LLVM-IR, or intermediate representation, which is then fed into the backend. And the backend is what is ultimately responsible for taking this IR and lowering it to machine code and generating your .o file. So here it is. I've opened up my main CPP JSON. You can see there's a lot more information in here. So quick ground you again. The individual zones themselves are not the important part right here. Just want to get you the general view of it. Again, we have the timeline on the top. But now importantly, this is a flame graph. So the purple bar, or the purple trace on top, that is the total time of executing the compiler. In blue, we have the total time spent in the front end, so how long we spent actually parsing and just generating this IR. And then way over here on the right is the time we actually spent in the back end doing optimizations and lowering their IR to an object file. So let's talk about Ninja tracing. Ninja tracing is an open source tool, Python CLI, and its main objective is to actually convert Ninja log files to the Chrome tracing format. Now, I mentioned earlier you can just, for some older versions of Ninja, you can just dump the .ninja log in directly. But if you're on a newer version of Ninja, specifically if your log file is version 6, you need to use Ninja tracing to actually convert it so that you can load it into Privett. But that's not all this tool does. It also has this it fills this missing link here. We have all this detailed information about our object files, and then all of these high-level what object files were built in what order, on what core. And it essentially stitches these two things together, creates a combined trace view of our compiler. And we can see that here. So here's my same build on 3 cores, and as you can see, I've got way more information here. I can tell you with some degree of certainty where time was spent during compilation. This is almost too much information, but it's good to have for now. So let's get into problems we can have in single files. So we're going to be light on code. So this is, hello world. If C++ was your first language, this might literally be the first code you ever wrote. We've all seen this. But I want to draw your attention to the hash include at the top. This is what's known as a preprocessor include directive. And what the preprocessor does when it finds a hash include is it goes out, searches for this IO stream header, and then essentially copy and pastes this code into your source file. It does this so it can have all your symbols and, great. But this is 69,000 lines of code that we are dumping into our source file. And if you recall, lines of code goes up, build times go up. And we can see this. We can kind of get another gut check here. So with Clang, and I believe GCC as well, you can do this capital E flag, and this will actually dump the preprocessor output of my main CPP here to a file. Well, I have to capture it into a file. And if we do a size check on these, we can see my original hello world, 4 kilobytes. No big deal. The preprocessor output, almost 3 megabytes. That is a massive increase. And here it is on the trace. I've kind of highlighted it here, the bolded scope, if you will. That is how much time in my simple hello world was spent just including IOStream. This is parsing the code that was pasted in from IOStream. This is almost 90% of my build. But that's okay, right? I mean, there's interesting and useful things coming in from IOStream. And I'm printing. I don't have exactly a complicated program. So that's not too surprising. But what do we do about includes in general? What am I recommending that you do? First things first, refactor your massive header files. So convenience headers are really nice for developers, but they're not so nice to your compilers and your build times. So generally, having smaller files gives consumers a better chance at including only what's strictly necessary for them. To channel Herb from his opening keynote, we want to give people the tools to explicitly express what they want to depend on. We don't want to force them to take this big box. We can let them take these smaller boxes of things. For declarations, this is another potential way of removing includes. It requires no external tooling, so that's wonderful. We could all do this today. It is frowned upon in some style guides if you define it for an entity in an external project. And in some cases, it can actually obfuscate dependencies. So, great tool for breaking includes in some difficult cases, but maybe not the best tool for all cases. It's a sharp knife. Use it carefully. Include what you use is maybe the most important takeaway here. The Include What You Use project has been out for a while, and essentially what it does is it tries to enforce that you are always including the header file that contains a symbol, the symbol definition that you are using in your source file. And this can mean that you have more and more includes in your source file, but fear not, we are already using header guards or pragma once, hopefully, so that we don't define the same symbol twice in a source file. So this is okay. The real benefit here is that it prevents us from including files that we don't use any symbols from. Your compiler has to parse everything that the preprocessor puts into your source code, regardless of whether or not you use it. It has no way of telling this code is useful or not before it has an abstract syntax tree. There's a flat cost of parsing. So that includes. Let's talk about templates. Templates are maybe the compilation performance boogeyman. If somebody tells you they've got long builds, your gut reaction might be something along the lines of, wow, you must have a lot of templates. And why is that? What's going on? So here I've got a really simple example, a template metaprogramming recursive struct called sum. And the intent of sum is when I pass in sum n, I get the total sum of the number -1 each iteration. So for example, here I've got a specialization of my sum struct, sum 5. So it'll be 5 plus 4 plus 3 plus 2 plus 1 plus 0. This program should print 15. But what's really going on? What does my compiler do when I specialize and I say, hey, sum 5? Well, there's this really interesting tool, another web-hosted tool, cppinsights.io. And the tagline of this site is to view your code like your compiler views your code. And when I put my small toy example in there, you can see there's actually explicit instantiations of my sum struct now. I've got sum 4, 3, 2, 1, so on and so forth. So the compiler is generating code for us. And this is code that we now have to parse. So what would happen then if I just put a massive number here into sum? Well, we'd get roughly 33,000 lines, depending on how you count it. And that is time that we will have to then spend parsing. This is not free. So template instantiation, in short, is a form of monomorphization, which is a really fancy word to just say to handle generic programming over generic types. Instead of using some kind of pointer indirection and kind of hiding the type behind something, we instead just generate explicit code with that type substituted for our generic T. So we're generating code. And we trade build times and binary size for faster run times. We don't have any indirection. This is explicit types. And this is a good thing, right? This is kind of a big part of the zero cost abstraction principle in C++. We want, in general, faster run times, and longer build times are just kind of a casuality of that. So what do we do about it? Well, the first thing is consider whether you need to even use template metaprogramming for your use case. As of CPP 20 and even earlier editions as well, constexpr and consteval can go a long way to completely removing the need for template metaprogramming in some cases. And, again, to channel Herb, is there a way to more directly express intent to the compiler? Template metaprogramming may not always be the best way to do that. There's actually a talk on this tomorrow morning, template-less metaprogramming. I assume it is on this based off the summary. I have not talked to the presenter. Next thing you should consider doing is to reevaluate your API. Do you need to be generic over that extra type? And what I'm referring to here with this question is, in some cases, when you have layered templates, one seemingly innocent specialization of a template can actually cause many, many, many specializations underneath. And this is what's known as a template explosion. So similar to the recursive sum template with 8,192, you could do something like that and not even use recursion. Which takes us to the last point. Can you just eliminate recursion in general in your template metaprogramming? Recursion is somewhat dangerous if it's unbounded. Thankfully, our compilers do bound it. There's f template depth, I believe it is. And I think the default is like 1024. So, okay. Those are not all of the single file problems, I will also say. Macros, inlines, there's a number of things, but I feel that templates and includes are kind of the two biggest ones. So let's talk about project level files, or project level problems. Well, the first thing, when we are starting out investigating our project level performance, build performance, we should use a tool called Clang Build Analyzer. Another command line tool. You point it at the build directory that was generated when you built with Clang ftime trace, and it provides a high-level overview of the hotspots in your build. This is things like files that took the longest to parse, templates that took the longest to instantiate, functions that took the longest to compile, and my personal favorite, the expensive headers in your build with the include chains. So not just this is a big header, but actually who included this? Where is this coming from? And it also has support for incremental builds. For most of this talk, I'm strictly talking about clean builds, but in some cases on really massive projects, you may actually want to profile and view hotspots for your small incremental compilation. Okay, let's talk about translation units. Translation units, briefly, this is not going to be a perfect definition, but it is the final representation of your source code before your compiler begins actually creating the abstract syntax tree. And this means that the preprocessor has run, template instantiation has finished, and I believe your inline functions are also expanded at this time. So here again, we have our sum struct. We're including IO stream, and we're putting it in this templates HPP file. Now, in my 3-source build, what if I include templates HPP, and I specialize the sum struct on 8192, and all 3 of them? Well, it's going to look something like this. We're going to have 3 big pink towers. This is just literally the specialization occurring 3 times for our 3 different source files. And you'll see the thick blue section with the twin peaks. That is, again, including IO stream. So this is happening 3 times for 3 source files. So the takeaway here is that include and template costs are per translation unit. Pragma once and header guards don't really help here. That's not what they're intended for. Their intent is to prevent duplicate symbol definition in a single translation unit. And we're talking about a larger build with more than 1 translation unit. So what do we do here? Are we just stuck? Well, thankfully not. There's thankfully been a lot of smart people who've been thinking about this for a long time. Modules are kind of the solution in some ways. So why do modules help? They eliminate redundant parsing. And they do this by, in short, this is not going to be a perfect explanation again, you build a source file, or you invoke Clang, you give it some commands or some flags to tell it, I want a precompiled header or a module, and when it's done parsing your code through the front end, instead of sending it to the back end, it will take that LLVM IR and write it out to a file. And then another Clang invocation in the future may see this hash include and say, oh, you know what, or this import statement, and I actually know where this is at. I'm going to go pull in this pre-parsed IR file and use it in my build. And worth mentioning for the sake of this talk, again, because we're specifically in Clang, precompiled modules implementation or precompiled headers implementation and modules are pretty similar. They share a lot of the same mechanisms. Of course, modules are more flexible, but in general, I'm going to use them somewhat interchangeably. So if we take our original example where we had 3 source files and we included templates HPP and specialized sum 3 times, but now we just use a precompiled header that simply has that content, include a templates HPP and specialize the sum struct. We now see that we've reduced the number of times that we have included IO stream and, again, specialize the struct. And our build is faster here, right? Before I didn't mention it, but it was 1.91 seconds. Now we're 1.16 seconds. That's a big savings. That's pretty cool. Unfortunately, this isn't the full picture. Well, we'll get to that in a second. So translation units, what do we do? Well, you can always use precompiled headers. Unfortunately, they're not a standard feature. Every major compiler implements them slightly differently. Thankfully, CMake does have a function called target precompile headers as of 3.16, I believe. And this function kind of helps paper over some of these differences between the compilers so you can maintain your build portability, but still take advantage of some of these features. And if you can, actually, you should probably just use modules if you're lucky enough to be on a C++20 compliant compiler. Now, this is kind of the big feature of CPP 20, but unfortunately, as of today, few compilers have full support for it. But again, there's going to be another talk tomorrow, unfortunately at the same time slot as the previous one, on CMake's approach to modules. So maybe there'll be some extra work to kind of taper over between some of these differences or different levels of module implementations. I'm not sure yet, but it's worth checking out. And then, so here's what I was alluding to earlier. Sometimes, unfortunately, it sucks, but duplicating work can be faster. I took my same example, and I've actually now turned it into a parallel build, which most of us, all of us, I hope, are doing with our builds. And you can see now that when I have a precompiled header, I'm actually building slower. And this is because Ninja cannot start building the other targets until my precompiled header is done. So I am just stuck waiting on 2 of my cores, even though I'm a parallel build. But if I just tell Clang, oh yeah, just duplicate this work, include this file 3 times, template 3 times, we're faster. But this isn't still the full story. Yes, we have 2 free cores, but those are free cores. Those are things that we can actually be building with. And so here's my same example again. Now we are linking to an additional library foo. It does not depend on my precompiled header. And you can see that I'm now compiling more code with the same resources, and my build times are somewhat similar. And this is just like a free win, right? We are building more code on the same amount of time. That's awesome. Let's get this into poor dependency management. So Alex Drew, who gave a talk yesterday with my coworker Milad, mentioned to me when I was going over the material for this slide, builds should be purely functional. And I really like this. The way I interpret this is that a single core and a parallel build should just work. You should not have any cases where you need to build twice to actually finish your build. If you run with too many cores, your build crashes. Like, that should not happen. Your build should always work, as long as you have CPU resources and enough memory. And you should strive to avoid large dependency bottlenecks. As we saw with our precompiled header example, this can actually force the build to be synchronous in some cases. So we just have dead cores, not dead, but cores that are being underutilized. And this is especially important when we're generating code. So protobuf, for example, if you have a target that depends on some protobuf header and another target that generates the protobuf header, well, those obviously can't be done in parallel. You have to wait. They are synchronous. And also, I should mention, the more cores you have, the more large dependency bottlenecks start to add up. With that said, you should generally prefer smaller targets. Just like with headers, it gives the consumer a better chance of only linking against what they actually want to. We can be more kind to our build system and let Ninja figure out where our dead time is and actually start building more things. So sorry for the text on this slide, but to try and put it succinctly as best as I can, explicitly expressed dependencies enables efficient hardware utilization while maintaining build correctness. Our build should always just work. We should do our best to put all of our dependencies into our build system so that we can lean on our build system to actually parallelize things. Quick water break. Okay. About halfway through here. Let's talk about include paths. So I mentioned earlier that hash include preprocessor directive goes out and finds the IO stream header. Where does it find headers? How does our compiler look for headers? Where is that? Well, IO stream is kind of special. It's a system header, or a standard library header, so the compiler knows where to find this. But for user-defined headers, where does it look? Well, this is what the -i flag in your compiler does, right? But what would happen if we pass -i a lot? So I ran a little experiment on my local machine. And what you're looking at here is I had 4 different buckets of include paths. And in each bucket, I ran my build 50 times. So n equals 50 for each one of these entries on the x-axis. One with 1 path, one with 10 paths, 100, 1,000. So with 1 path, the median of all 50 builds, 681 milliseconds, no big deal. 10, 689, that's not too bad. We get to 100, 735, okay, like it's sizable. We're noticing an increase, but that's 100 versus 1. That's a lot. It's not too bad. But when we get to 1,000, we really start to notice this. It's definitely scaling. We are slower, at least on first includes, when we have a ridiculous number of include paths. Now, hopefully nobody has thousands of include paths, but it's worth mentioning. So what's going on here? Why is that almost double? Well, I'm not totally sure, to be honest, but my understanding would be that interacting with the file system is not free. Clang has to go out and find these headers somewhere. It needs to query resources. It needs to talk over I/O somehow. There are caches everywhere for this. There's a kernel file system cache. Clang has its own file system cache once it's viewed a folder. But this still scales per translation unit, and it can still get expensive. So if I have thousands of translation units that have thousands of include paths to them, this adds up tremendously. Anecdotally, I have seen build time savings of, in the minutes, simply by removing 2 include paths from all of my targets in my build. I wasn't even using them. It's just free win, free build time savings. Okay, getting back to Privett again. Querying traces. I kind of call this Privetto's superpower. What it is once we have a trace loaded in Privett, we can actually write SQL queries to it and learn some pretty deep insights into our code base. So we can answer complex questions like, how much of the build is spent including this specific header? If you recall with Clang Build Analyzer, it was a lot of what are the most expensive, like top 10. But what if you know the top 10 headers and you know what's useful there and you have a hunch about your specific header? This lets you get in there and answer those questions. You can also write queries to determine things like what's the total impact on our build by using this external library? How many targets are including boost? So here's a small example. I'm not going to go too deep into SQL code here, but this is just to prove to you that you can query this, format it however you like, and you can reuse these queries on different traces. So you can write it once, reuse it over and over. So here I had a header where I included everything from the standard library up to CPP 11, and it was 1.8 seconds. So this is a flowchart kind of documenting my personal process of what I do on a project level to improve our build times. First things first, when you are working in this kind of environment, it's really important that you actually spend time measuring and identifying and be as empirical as you can. So this means running Clang Build Analyzer. This means checking Privett, checking what headers are expensive, and just really try to identify where are my expensive items. Once you've identified them, can you just delete them? No code is the best code. If you can, you have some good confidence that you have optimized your build in some way. Obviously measure again, but in general you'll be okay. Okay, we can't delete it. Can we refactor it? Can we remove half of the includes? Can we split this massive header up into smaller headers and then only include those headers at the call sites? Maybe. If we can, again, we have a good gut feeling that we have probably optimized our build. Always measure, but okay, we can't delete, we can't refactor. Can we just shove it in a module somewhere so we're only actually doing this expensive thing one time? If we can, same thing, maybe it's better. But if we can't, then we've kind of come to some conclusion. We know that this is expensive code, and it's important enough that we can't delete it. It's either already simple enough or too complex to easily refactor it, and it's not used enough to warrant putting it into a module. So then we just know it's expensive, and there's nothing really to be done. But now we know. This is my favorite slide of the whole talk. I love this slide. Is the juice worth the squeeze? Optimizing build times is a lot of work. All of the steps I just talked about would probably take most of us an afternoon to a couple of days to do on our code bases. And you can spend the same amount of time optimizing and removing things that would save you 2 minutes and things that would save you maybe 20 milliseconds. So we have to be careful with what we spend our time on. And that's why I implore you to focus on the low-hanging fruit. Identify your expensive code and tackle the big things. Spend your time there. Okay, let's talk about some higher order solutions. So the easy stuff is gone. All the low-hanging fruit has been picked. What do we do now? Well, can you just do less work in your build? If you're doing development locally, can you do an incremental build instead of clean building? Can you use a package manager and cache some expensive dependencies? Can you have some additional caching in your compiler using Ccache or some other open source library? Could you just throw hardware at it? Can we just get the company card, go to a computer store and buy some beefy laptop? Maybe. When that's not enough, can we spin up our cloud service provider and start distributing builds? Yes. These are very valid solutions. But it's a balancing act. Higher order solutions and optimizing your builds locally are not at odds with each other. In fact, they're in harmony with each other. So the title of this slide, What Andy Giveth, Bill Taketh Away, tongue-in-cheek reference to the 90s. Intel CEO was reportedly a little miffed that Microsoft CEO Bill was kind of, not taking full advantage of Intel's chips at the time because of their crappy software. It kind of evolved into what's known as the Andy and Bill's law, which simply states that new software will always consume any increase in computing power that new hardware can provide. So it's not simply enough to always just throw hardware at our builds. We will hit a wall at some point. Or over time, our software builds will get slower and slower because we don't feel the pain now of these big mistakes. And we end up losing a lot of the benefit that we first got when we moved to the newer hardware or the distributed builds. And then if you buy into Wirth's law, that software is getting slower more rapidly than hardware is becoming faster, you would then come to the conclusion that, yeah, this might actually not scale forever. We might get to a point where our code base is so large and it's so uneconomical to keep throwing more and more hardware at it, to keep adding more and more nodes somewhere, that we should spend some time optimizing locally. So like I said, higher order solutions and optimizing your build locally, those are two things that are in harmony with each other. They help each other. So some final takeaways here for you all. First things first, I want you to profile your builds. I implore you, spend an afternoon, get out there, look at it, just understand what is going on with my build. Where am I spending time? Again, compilation requires parsing of your source code, which is not free. Even headers that you include that you use nothing from, your compiler still needs to build the syntax tree from them. And that takes time. Better hardware won't always save us from ourselves. We cannot continually throw hardware at the problems. It will not always make things better. We are all stewards of our build time. A lot of us don't work at companies that have engineering teams sitting somewhere and on some other campus working on making our builds faster. And so we have to be cognizant of what we are doing. How are we impacting our build time? And then maybe also at the end, if you know a compiler engineer, maybe go give them a hug. This is not even close to the worst thing they have to deal with, but it is a glimpse into some of the madness that goes on underneath the hood. So I talk fast when I'm nervous, so I ended a little bit early here. But I just want to say thank you. Again, it was an honor being up here in front of you all. All of the examples from my talk are up on my GitHub. You can find me on LinkedIn. If you are interested in working at J&J, careers.jnj has all of our postings. Good team, great people there. And time for questions. Thank you. Go ahead.
Hi. just to mention a couple of things that I guess you didn't, and I'm not sure why in a couple of cases. Obviously, one thing that you can do to speed up your build times is maybe reduce your level of optimization or something like that. Like if you don't need to optimize to the maximum degree, don't put that work on your compiler, right? That's a simple thing. But on a more general level, what we find when we're compiling like very, very large projects is, and this speaks to like the issue that you have with trying to like include a lot of dependencies, like a lot of include files, or do like a lot of compile time processing. If you if you do like blob building, right, where you have one CPP, which just includes all these other CPPs, you're saving so much time on, compile time processing. You're just saving so much time on including, and it's just a really fast win. Assuming you're building everything and you're not incrementally building like single files.
It depends on the scale of your project, right? In some cases, how do I phrase this properly? You are right. Let me start there. That is a way to speed up your build, but it can slow down in some cases incremental compilation. If you make one small change to one of the headers included in that, that will then trigger this massive synchronous part of your build for this, giga module precompiled header, what have you. And that can be expensive.
Yeah, so exactly. So that, that's why when we're building in our pipelines, it doesn't make a lot of sense to build incrementally there. But when we're building on our own machines locally, that's a different situation. Mm-hmm. I just wanted to bring up those points.
Yeah, no, those are good points. Thank you.
Thanks for the talk. Really exciting to see people. Always exciting to see people talk about speeding up builds. You mentioned some of the pros and cons about forward declarations. I wonder if you had any experience with, instead of forward declaring something from another library, if you can have each library provide, say, an _fwd.hh that gives like authoritative forward declarations, and then that can be a way to scale better. Mm-hmm. If the real header includes the forward header as its first file, that can catch sometimes when one changes, they get out of sync, right? Some of those instances will cause build breakages. So I wondered if you had any comments on that technique.
No, that's a very valid technique. Boost does this a lot. I've actually seen Boost variant is the example I've run into, where I saved a lot of time by just simply using the forward declaration of variant versus actually including variant. So yes, that is true.
So a large part of your talk is talking about the time issues, right? But I've seen where we have problems with space, where the compiler takes a ton of memory. And largely maybe they're correlated. But I'm wondering if you were aware of any tooling to look at, like, why is my compiler using so much memory for a particular translation unit?
I'm so happy you asked this question. I actually prepared a slide for this. So,
perfect, thank you.
Yeah, so in short, there is some work on this in LLVM, but there's nothing available today. This specifically for profiling memory. And you had a question before that slightly. What was that?
No, I think that's pretty much all my questions.
Thank you.
Thanks.
Oh, hey. I'm sorry, guys. 1 sec. Sorry, I didn't see the slide. I wasn't looking.
Sorry. Have you also looked at one thing I've done with helping to improve performance is if you have one TU that is taking up a lot of time, especially if it is a class, you can move the implementation of the expensive methods to their own TU, and then at least you can get that class parallelizing against itself.
Yes. This is another very valid technique. I can't go over all of the possible solutions to making to make compilation faster, but yes, there's also been some work on, I think it was TP Build was talking somewhat about this, where they were mentioning that they were trying to do this automatically, because as you can imagine, doing that is kind of a manual process, and now you have to like synchronize changes between files. It can be a little bit annoying.
Yeah. And then have you looked into one thing I've been interested in, I work on CMake.
Yeah.
Optimizing the Ninja build graph has been something I've been looking at over time. is trying to do some kind of metric over the graph for available parallelism. So you can just like look like how wide is this build graph in terms of cores? Like if you have more than 64 cores, it doesn't make sense because nowhere is it ever wider than 64. Because that could also help with Unity builds. You could measure and be like, oh, if you Unity build like 4 here, you can, help that. Because if you do Unity too much, you'll make more bottlenecks.
Yeah, exactly. I kind of subtly alluded to this when I mentioned dependency bottlenecks. The more cores you throw at this, you can't always take advantage of everything, right? Like you mentioned, how wide is your build tree, or dependency tree? And could you write a SQL query to do this?
Yeah, it's
maybe
very graph theory heavy, and I haven't found an algorithm for it, but
I mean, you have all of the information available to, in theory, do this.
yes.
So, but you don't even need anything more than the Ninja log file for that.
Yeah, because you need the time of how long each node.
Yeah, you don't care about what's going on inside of it. Yeah. Yeah, in theory, that sounds cool.
Yeah.
Thank you.
Hey, thanks for the talk. I just was kind of wondering if you had an example of one of those times when the result was, well, it's just expensive.
I do. I'm not sure if I can really get into it, unfortunately. I have seen this with third-party libraries, where the value of using a third-party library outweighed the build time it costs me because of the flexibility included with it. Sorry, I can't be more specific. Go ahead.
Hi, long-time listener, second-time caller. So I might have missed it, and I'm sorry if I did, but one technique that we've also found really valuable that falls into this refactor bucket can be the pimple pattern pointer to implementation. You got a lot of headers in your HH file. You can move some subset of them to the CC file and save a lot. There's a lot to be said, I think, about how to do this. If you just use a standard unique pointer, then you have to declare the destructor in the header and define it in the CC file, but then you can't rule of 0 your class, but there are ways to do that. But then they come with a space penalty, but there's ways to get around that. There's a lot to be said here. But yeah, I just wondered if you found value in the pimple pattern here.
I haven't used it in my code bases. In theory, based off what you were talking about, it sounds like it could be useful, but I don't have a more definitive answer.
Yeah, the other thing too is that it can cost, it'll cost a heap allocation, so you need to balance that. That's kind of one of the main trade-offs. But yeah, it's been like, where it's useful, it can be very useful.
Yeah, as long as you measure and you know exactly where the cost is, one time, a lot of work, big savings.
Measure, measure, measure.
Yes, sir. Hi.
Hi, I'm curious in your opinion about forward declarations, because if we follow your advice of avoiding huge include files to the extreme, then we have very little include files, and you literally cannot use anything from that file without also using its dependencies. In that case, do forward declarations actually help?
Yeah, I mean, so I didn't want the takeaway to be that forward declarations are never useful, but more so that if used incorrectly or maybe prolifically across your build, you could run into some more annoying problems. And when I say to use smaller header files, it's not to decrease the total number of header files. It's to take your large header files and maybe split them up so you only have, say, like one struct per header, for example, if it's a useful struct. And yeah, I mean, again, forward declarations are not necessarily inherently bad, but they can be abused. So just be careful with them.
Thanks for the talk. I have a question. I saw that you mentioned protobuf bottlenecks your build, and it does bottleneck my build. Do you have any recommendations or feedback, like anything I can do to fix that?
Yeah. So something I have seen done is to create one target for one protobuf, which it kind of sucks. Like it's very difficult to maintain if you have lots and lots of protobufs in your build. Again, you could start employing things like a package manager and just kind of try to put that extra effort outside of your build, because hopefully your proto definition is not changing super often. But yeah, I mean, at the end of the day, you do need to generate these files based on some proto, and it will be synchronous for your other targets. So.
Thank you.
Yes, welcome back.
Thanks. It's good to be back. One of the, I think, most important, most impactful things, like, okay, we go through this effort of refactoring or doing these other things, and then we get the build fast, and then we turn our attention to something else, and the build creeps up because nobody's paying attention. So we've had a lot of success with some kind of like monitoring, but even though it's been successful, it's quite crude. So I wondered, have you been experimenting with like monitoring known problem files or monitoring the overall build in some way? And what are your thoughts on that?
Yeah, so that's actually how I got into this work. I felt like an increase in build times had happened, and I wanted to kind of get some data about when and where that happened. And so we actually ended up doing this quarterly. So every 3 months, we'll just do every successful nightly build, plot it, what was the total build time of some stage. Obviously, because you have a big build matrix, it's hard. So kind of like our main build on our main target. What was the build time every night that was successful? And then we plot that. And that's how you could see the kind of like jaggedy line before. And so yeah, I recommend doing that quarterly. And then also, if you can, kind of embedding in that plot the commits that the build was from, so that you can go in and see like what's the delta between this successful build and this successful build, and I saw a big increase or a big decrease. What happened? Why did this change? So yeah.
Thanks. Yeah, we have not been doing it like quarterly on the whole build. We've been doing it like weekly on like known problem files, but I would really like to learn how to go from doing it weekly to doing it strongly.
Yes. You can always automate these things with Python scripts. If you're using pretty much any web hosting for any Git project, you can write queries, HTTP queries for these things and automate it in some way. And you could change that from quarterly to daily if you really really wanted to and had that kind of throughput on your commits.
Yeah, it almost feels like a data viz problem, honestly. Like you can get a lot of data, but then how do you get to the insights? Anyway, YouTube listeners, if you have any ideas, please drop a comment. I would love to see it. And don't forget to hit like and subscribe to CppCon. Thanks.
Thank you. What a good one to end on. Thank you, guys.